Hello and welcome to AB 474 Indoor Environmental Control. This is our fourth installment of the Psychrometrics series on the study of moist air. So far we've reviewed some foundations, including the ideal gas law. We talked a little bit about pressure and measures of pressure, and we've reviewed the psychrometric properties. The point we're at now is where we are discussing how do we determine what the properties are. As we said at the end of our last session, if you know two properties, then you can find all of the others. So if you're given two properties, you can determine the other properties. So what methods do we use to do that? So calculate with equations. So we have a set of equations, and in this case we actually have our textbook as a reference, and then I've given you two other references, one from the Handbook of Fundamentals from ASHRAE and the other from another textbook, and those are available on the wiki. Each of those references uses, unfortunately, a different set of variables. So what I've also included on the course wiki is a comparison chart of the variables that are used and the symbols and the equations provided in each one of those. And as part of this lecture, we're not going to review every single equation. We're going to use them in an example in a few minutes, but we're not going to review every single equation for every single property. But I would like for you to do that on your own. And again, so you have a column of equations and variables from our textbook, from the other textbook, and from the Handbook of Fundamentals. So I encourage you to spend some time with this and spend some time becoming familiar with the parameters and the equations and the variables that are used inside of each one of those. Okay, and so this is a two-page document. We've already reviewed what each of the properties means, and now you need to spend some time with the equations. And like I said, we'll do an example in a few minutes where we'll use the equations. So I guess the gold standard method is to calculate with equations. Now we have a variety of forms that we might see those equations. So we have psychometric tables. I'm not going to demonstrate those for you in this lecture, but they exist. You can find them. We have the psychometric chart, which was introduced briefly at the end of the last session. And then we have calculators, so that are based on computer programs. What's important to recognize is that all of these last three possibilities are just different ways of representing the equations. So everything goes back to the equations in terms of calculating our psychometric properties. And what I think is the best use of time for this is to do an example. So we'll start with the psychrometric chart. And recall, for the psychrometric chart, this is a graphical representation of the moist air properties, and each chart is for a specific elevation or a specific atmospheric pressure. What you'll find is the same thing for the tables. It's very similar to the chart. This is just in a numerical form, and this is in a very visual form that we'll take a look at in just a moment. Most computer programs allow you to at least have the capability of allowing you to adjust your atmospheric pressure, which gives you some more flexibility in the application of that method. Okay, so we're going to work through an example, and we're going to work through the same example and use multiple methods. So we're going to use the equations, we're going to use the psychrometric chart, and we're going to use an online calculator in order to get the psychrometric properties. So here's our example. We're given a dry bulb temperature of 27.4 degrees Celsius. We're given a relative humidity of 43%, and we're given an atmospheric pressure of 92 kilopascals. We're being asked to determine all of the psychrometric properties. Using the psychometric chart. Often this is called the psych chart, so we'll start abbreviating it occasionally. So the psych chart, using the psychometric equations. We're going to calculate this by hand. And using a psychometric calculator. Okay, so the first method we're asked to use is a psychometric chart, and I've provided you with several different variations of the psychometric chart on the wiki. For the most part, we're going to go to the psychometric charts that are produced by ASHRAE for our examples, and that's what you'll be given on your exams as well. So, as I mentioned in the last session, until you're accustomed to looking at this, it can be very intimidating. So let's orient ourselves. Recall that on the x-axis is our dry bulb temperature, and we're looking at a dry bulb temperature of 27.4 degrees. So let's go ahead and find that. So this is 25, 26, 27, and this is about 27.4. Okay, and our relative humidity lines, remember, are the curved lines. So we're going to look for 43%. So here's our 40% line, and this is our 50% line, so we're going to go not quite halfway in between, and I've gone ahead and marked it here just for simplicity's sake for us. But we come up our dry bulb temperature to a line of 43%, and we mark it, and then from here we can look for all of our other properties. Let's start with humidity ratio. So we want to go all the way across here to our humidity ratio, and we see we have a number of 10. I would encourage you, anytime you're using a psychometric chart, to take a look at your labels and pay special attention to the units, because not every chart uses the same units for the numerical values along the grid lines. So be sure that you pay attention to the labels on here. And in this case, it's grams of moisture per kilogram of dry air. So 10 grams of moisture per kilogram of dry air. Okay, so we have that one. Now let's take a look for our specific volume, and that's this slanted line here. I'm going to come over to here. Okay, this line is 0.92, 0.9, 0.88, 0.86. So we're between 0.86 and 0.87, so about 0.865. And then we would also like to take a look at our wet bulb temperature and our dew point temperature. Okay, recall that our wet bulb temperature are the slanted lines, and our dew point temperature are the horizontal lines. Okay, so first let's go all the way over straight across here, and when we hit the saturation line, this is going to be our dew point temperature. And these are our labels, so 10, 11, 12, 13, let's see, 10, 11, 12, 13, 14, 15. So we're not quite spaced evenly on here with each of the individual lines. So recall that we have two sets of lines that are almost on top of one another. So we have enthalpy. Enthalpy are these lines, and then we have the little dashed lines here are actually our wet bulb temperature lines, which the intersection of the dashed lines and the horizontal lines give us our saturation temperatures. So the dashed lines, where they match up to the horizontal lines, should give you the same temperature line. So 10, 11, 12, 13, 14, 15, now they match up, okay? So for our line, if we go all the way across here, let's trace it across. So we're landing somewhere just below 14, so let's go ahead and call it 13.5. If you say 14, that's okay for our dew point temperature. And then if we want to take this and extend it out along the diagonal line, that will give us our web bulb temperature. And we're between 18 and 19. So this is 20, 19, 18, and we're landing somewhere right in here. We're going to call it 18.5, 18.8, somewhere in there. I've called it 18.8, but if you're close to that, then you're okay. One of the things you'll realize with the psychometric chart is the most likely error you're going to have is reading the chart. It can be very tedious, and so human error is the most likely thing you're going to come across in terms of errors. The last thing we're missing is our enthalpy, and so we need to pay attention to the solid line. It doesn't extend out through the chart, so we kind of have to visually extend it ourselves. I'm going to kind of go down the 50 line and say, okay, well, we're above 50, 52, 54, 56, 58, 60. Okay, so each one of the marks is 1, and each one of the full marks is 2. So we're above 50. We're a little bit above 52, so let's call it 53 kilojoules per kilogram of dry air. All right, and now we have all 7 of our psychometric properties, and I've gone ahead and summarized them on a chart. So we're going to compare the results that we get from the psychometric chart and from our equations and from our online calculator. So I've gone ahead and put our results into our summary table, and next we're going to take a look at the psychometric equations. Okay, so if you have reviewed your psychometric equations at this point, you'll realize that the first calculation that you have to do is the partial saturation water vapor pressure, so that little piece of S that we talked about before. So we are working in this example in metric units, so we want to make sure that we grab the equations that are for metric units. That's one thing you'll want to pay attention to in your equations, is which units those equations are written in, because you will get the wrong answer if you use the wrong set of equations that are in the wrong units. So we are going to take some of the first equations from the Albright text to get these to get our initial pressure. So our saturation water vapor pressure one of the easiest ways to do it is the equation that's given in the Albright text. And we're going to use equation 2.1 to start with. And if you've taken a look at it, you'll realize that it's a lot of coefficients and an exponential equation, and it factors in the absolute temperature. And I'm not going to write out all of the coefficients for you, but I will write out the equation. Okay, and we know that our temperature is 27.4 degrees C, which is 300.55 Kelvin. So if we plug that in, we get our partial pressure, saturation water vapor pressure is 3.651958 kilopascals. Okay, so I suppose I should go ahead and label this equation as well. So this is our partial saturation water vapor pressure, and earlier we were labeling this little piece of S, and the Albright equations, they put a big piece of S. Other ways to get this value, so let me say, or if we don't have this equation available, or we want to find other ways to get this value, in our book they don't give us this equation. What they give us instead is table in the appendix, in Appendix A, Table A1B. And in Table A1B, at 25 degrees C, this value is 0.00317 megapascals. And at 30 degrees C, it's 0.00425 megapascals. And so you can interpolate between those two in order to determine that at 27.4 we're going to get approximately 0.003602 megapascals, which is approximately 3.602 kilopascals. And you can see that that's not exactly the same as we got from this equation, so that approximation has some errors associated with it. There also is another equation that we might use. We're not going to talk about it in this class, or at least in this lecture for the class, but you should be aware of it, and you might want to employ it as you make your own psychometric calculator, and it's called the Teton equation. Okay, so we have our saturation vapor pressure, and now we need to get our water vapor partial pressure. So sticking with the same format, I'm going to stay with the Albright equations for now, and we're going to get our water vapor partial pressure. And we'll use Albright equation 2.2. And it's just the relationship between your saturation pressure and how saturated you are. We know that our relative humidity is 43%, so we're 43% saturated. And so we get our result for our water vapor partial pressure. Now we're ready to calculate our first property, which is, in this case, humidity ratio. We can stick with the Albright equations, but we have the same equation both in our textbook and in Albright. So in Albright, it's equation 2.7, and in your textbook, it's equation 3.14b. And it's a coefficient times the relationship between your water vapor partial pressure and the partial pressure of air. And we haven't yet solved for the partial pressure of air, but it is our pressure minus the part made up by vapor, and the remainder is the part made up by air. Okay, the next property that we want to calculate is our enthalpy. And we have an equation from Albright, 221. I'm going to draw a star beside it because that's the one we're going to use and go with. We also have an equation in your textbook, but there's a little discrepancy between the two of them. And we'll identify that in just a moment. 320B. Okay. So in the Albright equations, the coefficient for the dry bulb temperature in this part of the equation is 1.805, and in the HVAC text, that coefficient is 1.86. And so if we plug in the numbers and calculate, we end up with a different result, depending which one of those coefficients we use. And so the question you're probably asking is, which one of those is correct? The answer is they're both correct. So that brings us to a good stopping point to talk about where do equations come from when we're looking at calculating our psychrometric properties. There's two different ways that we can get equations. One way is deriving equations based on theory, and the other way is developing equations from empirical data, so fitting curves, predictive curves, to a set of data. Our psychrometric properties are derived from fitting to empirical data. So the reason that we end up with discrepancies between the two coefficients is it depends on what data were used over what range and what methods were used to fit a curve to the data. And so for some scenarios this may give a better fit, and for some scenarios this may give a better fit. So the error that comes from applying these is going to vary depending on the scenario, the set of circumstances you're applying it to. And that's the extent we're going to discuss it in terms of introducing the equations. And as far as this class is concerned, either of those is correct. So the next property that we're going to calculate is our specific volume. And in Albright, it's equation 216. And there is also an equation in your textbook, which is equation 3.1. And but it requires a little bit of a derivation to get to the form that we're going to use from the Albright text. And so if we plug all of our values in, then we get a value for our specific volume. I would encourage you to go back and plug the numbers in and do the calculations for yourself. I don't want to use our time in our lecture for that, but I would encourage you to pause and run the calculations to make sure that you know where to pull the numbers from and make sure that your units work out the way you expect them to. Okay, the next thing we're going to look at is our dew point temperature. And in Albright, that is equation 218, and your HVAC book doesn't give an equation for this one. Make sure I get all the numbers in here right. This one's a long one. 35.9. Okay, and then if you plug that in, 6 degrees C. All right, and then the last property that we're going to calculate is the wet bulb temperature. And wet bulb temperature is, in my opinion, the most difficult. The most difficult property to calculate because there is no direct calculation for it in our typical equations. So the method that's described in Albright's text is an iterative approach. And this iterative approach looks at our enthalpy at saturation. So we're going to employ that equation, but we're going to do it at saturation, which is related to our wet bulb temperature. So this star means saturation on each of these equations. So not the actual condition we were at, it would be the condition if we were at saturation. because recall, wet bulb temperature is where we would be if we were at saturation based on evaporating moisture into the air. Okay, and then the second one is another approach to the same value. And this one does include our current condition. Okay, so with both of these equations, when we use the S, it means saturation. So S means saturation, so it's the condition at saturation. T star is our current guess for wet bulb. And then the enthalpy star is enthalpy that's been calculated for the current guess of wet bulb temperature. And then our humidity ratio at saturation for our guess is our humidity ratio at saturation for our current guess. Which really means it's our guess for whatever our wet bulb guess is, and a relative humidity of 100%, so at saturation. And then essentially you have to start with a reasonable guess for your wet bulb temperature, and then you revise that guess until the resulting difference between these two is acceptable to you. So let's do an example for, let's apply this to our current example. So let's guess a T star, and let's just start with a guess of 20 degrees C. And then we're going to calculate saturation partial pressure, the humidity ratio, and then the saturation enthalpy based on the X1 calculation and based on the X2 calculation, and then we'll look at the difference between those two. Okay. All right, so for our first guess, we're guessing 20 degrees Celsius. We get the saturation pressure, and then we get our humidity ratio at our guess. And then we get our calculation for enthalpy by each equation. And then we get our difference. And we'll say that's not good enough, so let's do another guess. And we're going to guess 18 degrees Celsius. Run through the same equations again, or same calculations again. This time I'm going to write all the units out. It should have the same units as the row above it. And we did get closer together. And for this case, we'll say that's close enough for our example that we're working on. So what are some of the strategies for what to pick as your initial guess and then which direction to move? I like sketches, so we're going to sketch just a basic psychrometric chart here. And this is our dry bulb temperature at whatever our state point is, and our wet bulb temperature, and our dew point temperature. So one strategy is to start at the highest possible temperature for your wet bulb temperature. And another strategy is to start at the lowest. So what is your highest? Your dry bulb temperature. And what is your lowest? Your dew point temperature. So those are two strategies. There are a variety of other ways you could choose your starting point, but those are two ways that give you a logical way. So if you start at the lowest, then you move your way up, and if you start at the highest, you move your way down. All right, so let's go back to our summary. And let's add in our calculated values. And the last thing that we're going to do is go to an online calculator and grab the results from that. Okay, so let's see if I can do this with my recording device here. Alright, so this is one of the links that I gave you on the wiki, and this is a psychometric calculator that was created by Dr. Richard Gates and one of his former students, Dr. Hanzong Zhang. And it's a pretty simple, low-tech in terms of being pretty with the interface, but very nice coding behind it. Calculator, and so you select your inputs. We're going to put in dry bulb temperature and relative humidity, and we're going to use SI units, and we'll just say we want it to output everything. So we select our inputs and our outputs. Our dry bulb temperature is 27.4 degrees Celsius. Our relative humidity is 43%, and in this case we can change the pressure, which is very nice. And our pressure from our example, should I type it in correctly, is 92 kilopascals. And then we ask it to calculate for us, and we can see the result here. And we'll go ahead and write those down. So wet bulb temperature, 18.3%. or 18.3 degrees Celsius. And our dew point temperature is 13.8 degrees Celsius. And our enthalpy, 55.1 kilojoules per kilogram of dry air. Our specific volume is here at 0.95408 meters cubed per kilogram of dry air, and our humidity ratio here is 0.010801. Kilograms of water per kilograms of dry air. And then there are a number of other values that we're not going to look at today for this class. All right, so let's get back to our summary. So I went ahead and included the results as we were reading them off from the online calculator. And if we want to take a look, what we can see is that our results from our equations by hand and our results from the calculator are very, very similar. There are a few discrepancies, so a little bit of difference in the specific volume, not so much difference in the enthalpy calculation, and so there you go, enthalpy calculation, and so that's indicative that they probably used the same equation that we did with the same coefficient that we chose. We can see some variability when we use the psychrometric chart. So the temperatures look pretty similar, but when we get down to specific volume, which is the inverse of density, that's where we see the biggest difference. Now let's think for a minute, what is different about the psychrometric chart from both the equations by hand and the calculator? The chart that we used is a chart for sea level. So let's go back to our chart and just take a look. Right there, our chart is for sea level, but our atmospheric pressure tells us we're not at sea level. So we're not at 101.325 kilopascals, we're at 92 kilopascals. So the results from the chart aren't that far off, but they are further off for anything that can be more heavily influenced by pressure. So density is more heavily influenced by pressure, and so we see more discrepancy between the two because of the difference in pressure at which these values were attained. That is going to wrap up our kind of example where we're looking at how do we determine our psychrometric properties. And the next thing we're going to move on to are psychrometric processes. So we'll start to look at how do we get from one state point to the next, and that will come in the next segment.